energy entropy bounds, energy and entropy bounds. So the idea is that in quantum field theory, the energy, relativistic quantum field theory, the energy is always positive, but energy density can be negative. The energy in some piece of the space-time, some region of the space-time, can be negative. However, it cannot be arbitrarily negative, and there are some bounds on the energy that are usually related to entropy. So the bounds are relate entropy and energy. And we will see that a new information theory quantity that is called the relative entropy will play a major role here, and also that this subject is much more related to gravity, to ideas of thermodynamics in gravity, black holes, that smoothly connect with some properties that are of theories without gravity, for the limit of g going to 0. So let me start with the Bekenstein bound. Bekenstein bound is the oldest of these type of bounds, and it's based on an idea based on black holes. The idea is that suppose you have a large black hole here, and I put some probe outside of it that is held in its position by some line or something, and then you release the probe and is swallowed by the black hole. So the idea is that initially you have some entropy for this object, and then after it is swallowed by the black hole has increased its size, has increased its entropy proportional to the area, and there should be that the final entropy has to be greater than the initial entropy due to the generalized second law. That is just the usual second law, assuming that the black hole entropies are normal entropies of objects in the theory. So this gives you this type of inequality, that the change in the area of the black hole has to be greater than the change on the entropy of the object outside. And if you think that this object is very small, it's just a probe object, it doesn't do much back reaction, then we can compute using the Einstein equations how the area changes. And the area changes as in the first law of thermodynamics. This is a first law of thermodynamics in presence of black holes, and the area changes just as the change of energy divided by the temperature of the black hole. So this is just pure geometry with the Einstein equations. If you look at the black hole space-time, this energy is the energy measured at infinity. So it's a real energy of asymptotic observers, but this belongs to a Killing symmetry of the theory. So it's the energy, the charge of a Killing vector. And if you compute it the same symmetry, but very near the horizon, this looks like a boost in this region of the space-time, right? So if your object was very near the horizon, this change of asymptotic energy is in fact given by this expression. Here I'm taking some coordinates near the horizon that look like coordinates for flat space in Minkowski space. So this x1 is the distance to the horizon, and this is the stress tensor, the energy density. So we have seen this expression before. This expression is just the modular Hamiltonian of Rindle space. And it's not surprising because here we have a state that is somehow thermal with respect to asymptotic observers, asymptotic time-like symmetry. And if we go very near the horizon, we see the state is approximately vacuum. So it must be the case that this modular energy is proportional to the Rindler modular energy. So, and this connects the idea of Unruh temperature for these observers with the idea of Hawking temperature if you see the black hole very far away. So then we can compute this quantity, the change of area divided by 4c, by computing in the limit where the black hole is very large and you are near the horizon. You can think directly that you are near the Rindle horizon in flat space, and you can compute this quantity by computing the change in the modular Hamiltonian, the change in this operator. So the inequality turns out to be this one, that the change in entropy is less than the change in the energy multiplied by the distance to the horizon. And Bekenstein, in his original paper, thought in classical terms as objects, macroscopic objects, and he thought, well, the change in entropy will be just the original entropy of the object, and then when the object is swallowed, there is nothing more outside, so there is nothing. So the change of entropy is just the entropy of the initial object. And this thing you can approximate by saying that is the distance to the horizon, this r, that is more or less the size of the object if you put it very near the horizon, times the energy of the object. So it's an approximation, let's say. And so this is the way Bekenstein proposes his bound. You see that this bound does not depend at all on G. You started with black holes, but you end up with something that should apply to flat space physics. And it looks rather strange from the point of view of flat space physics, because it tells you that the entropy of something is always bounded above by the size of the object times the energy. So it looks like a kind of universal bound on the number of degrees of freedom, because the entropy cannot grow. If you keep the energy fixed, the entropy cannot grow much. And you can see that if you have, for example, many species of particles, independent particles, then the entropy can grow because of you have a more phase space available because of the number of particles, while you can keep the energy fixed, and somehow this will prevent your theory to have too many degrees of freedom, too many different types of particles. So it was rather surprising from this point of view. But now let us come back to this form of the bound that is a little bit more precise when you think in quantum field theory. You have instead of, because what are the problems? There are evident problems with this. First, you have to define what is R here. Second, the energy, if it is the energy on only half space on outside the black hole, can be negative. We know that it can be negative. So, but the entropy can never be negative. Or if the entropy is localized, for example, the entropy is outside the black hole, is the entropy of the outside part. If you include the quantum corrections, there will be vacuum fluctuations that make the entropy divergent. So how can this inequality hold if the entropy is divergent? So in order to repair that, we have to go back and try to understand the derivation itself again, and we see that this term here is better expressed, of course, by this integral in quantum field theory. So this, we keep it as it is. And in the change of entropies, if we think it's only outside the black hole, you have to take first the entropy of the object plus the vacuum outside. So the whole thing, the whole state outside, minus the entropy of the whole state outside when the object has been swallowed by the black hole. So it's a change of entanglement entropies. It's a change of entanglement entropies outside the black hole. So the correct expression of the bound that is derived from this thought experiment is this one, where this is the now where I'm thinking just in a flat space limit, and so it's a change in the modular Hamiltonian of Rindle space is greater or equal than the change of entanglement entropy in the half space. Now we want to prove this, if this is correct. And for that, we introduce this quantity that is called relative entropy. That is a kind of information quantity, but now depends on two states. And the expression is this one. The first piece look like minus the entropy, the von Neumann entropy of rho, but the second one involves rho 0 and rho, so it's not an entropy, it's something mixing the two states. In order to have some more easy understand what this means, you can add and subtract the entropy of rho 0 here inside, and then you can these two terms, calling minus log rho 0 as a modular Hamiltonian. You know, this is the modular Hamiltonian of the state rho 0. Then this is the change of expectation values of the modular Hamiltonian. And while these two terms are just the entropies of rho 0 and rho, so this is minus the change of entropies. So the relative entropy is delta K minus delta S, the change of energies minus the change of entropy. It's very much like, it's like a difference, it's kind of a difference of free energies, energy and entropy sum, combined. So the KR, of course, is the modular Hamiltonian of rho 0. So this is not exactly, it's not symmetric between rho and rho 0. There is a difference here. Here, K is the K of rho 0, is the second one. And it turns out that it's not difficult to prove that the relative entropy is always positive. It's always positive for any two density matrices. So, and this gives you the quantum Beckett bound is true, because apply the inequality that this is positive to the case where the region is the Rindler space, you have just this inequality. That was what we wanted to prove.
Horacio, sorry
yeah.
to interrupt you. We have a question on the chat. Do you want I read for you?
Yeah.
So the question is, I would have said that your expression for delta K in terms of the integral was just the exponential of val of the modular Hamiltonian, of the value of the modular Hamiltonian. Where do I see in the integral that this is a delta?
This is a delta, sorry. Okay. No. Okay, sorry, yes, I understand the question.
Sorry, the expectation value of the modular Hamiltonian, yes.
Yeah, this delta K is in fact the variations of expectation value of the modular Hamiltonian between two states. Here I am applying it to the case where the one state is the vacuum itself. So I'm subtracting the expectation value in the state, in some state, arbitrary state, that is this expression, minus the same thing for the vacuum, which is 0, because the expectation value of the model of T0, 0, the energy density in vacuum is 0. Or you can say, well, I have somehow renormalized my expectation value of the stress tensor such a way that is 0 in vacuum, which is always what we do, right? That's answer the question, I think.
I think so, yes.
Yeah. So, but well, then the proof is very easy, but then we have to understand what does it mean, this. Well, for that we have to understand what does it mean relative entropy. And relative entropy is a very important quantity in quantum information theory. Is in fact much more important, I would say, that the entropy itself. In fact, is well defined even for the algebra for quantum field theory that are these strange algebras, type 3 algebras, where the entropy is always divergent, but the relative entropy is well defined, and it's a measure of distinguishability between two states, the two states. It has some important property. This is not only positive, but it's always increasing, monotonically increasing if we increase the algebra where you see the two states. Because of this idea of distinguishability, if you have more operators to distinguish states, you have more relative entropy. In particular, for example, the mutual information that we have talked about is a kind of relative entropy. It's the relative entropy. You have two algebras in tensor product, and then is the relative entropy between some state in the two algebras and the composed states as in tensor products of the two states reduced to each one. This is the mutual information that we have seen that is well defined and finite in quantum field theory. And the monotonicity here, the monotonicity under increasing of algebras is equal to strong subadditivity that we have used in the last lecture. But a more operational meaning to this idea of distinguishability is that if suppose you have the two states and you want to distinguish them by doing measurements, then you can try n measurements, the best ones devised to distinguish the states, and you can see that you can confound the two states probabilistically after n measurements with an error, with a probability that it falls exponentially with the number of measurements, and the coefficient in the exponential is just the relative entropy. So if the relative entropy is large, with very few measurements, you will distinguish perfectly well the two states. If it is small, it will be hard to distinguish measuring the two states. So, but then what does this tell about the Bekenstein bound? It tells something very different to the original idea of Bekenstein. So the Bekenstein bound is not a bound on the number of degrees of freedom, but rather on the ability to distinguish an object from the vacuum fluctuations if the object doesn't have enough energy, let's say, in a region. So if you keep looking only at a finite region of space, the vacuum fluctuations will perhaps difficult us to distinguish a state from the vacuum. But it doesn't mean that your theory cannot have, for example, many degrees of freedom. In fact, the problem is exactly that. If you have many degrees of freedom, the vacuum fluctuation will be very large. So you will have delta S. So the entropies of the vacuum and the object, both of them will be large, and delta S will be saturated by this quantity, by this energy. So in the limit of a large number of particles, for some states, you will have equality, but you will never be violated the inequality. Another comment is that there is no new physics coming from gravity, from this idea of black holes, but rather the bound is valid in quantum field theory without thinking in gravity. But it's nice that the two things converge to the same. So, and why is that? Is because of this pre-established, if you see how the bound holds in quantum field theory, it's very important, this pre-established relation somehow between entropic quantities and energy that is given by the model Hamiltonian of Rindel space, that is very particular and is related to energy density.
So we got a syntax question about the meaning of confounding. I guess you mean confusing also, right? It's just
yes, sorry. Yeah, maybe it's wrong.
No, it's the same, I believe.
Okay.
English-wise, it should be okay.
Okay. So, okay, let me then continue. So I come then to what is called the first law of entanglement entropy. That is the analogous thing of the first law of thermodynamics, delta S equal to delta A. That is, suppose you have a state, and then you perturb the state by very small amount in order to keep the trace equal to 1. This delta rho has to have 0 trace. And then you just expand the expression of the von Neumann entropy, and you get that the change in the entropy is given by this expression, which is, if you see, it's just the change of the expectation value of the model Hamiltonian. So under perturbations, the change of entanglement entropy is computed by the change of the expectation value of the model Hamiltonian. It's exactly the same as this formula, that is just a particular case, this formula for thermal states. You can say also that this has to be true because the relative entropy, that is the difference in these quantities, if the two states are the same, is 0, so these are 0, and it's also always positive. So if you change linearly, the one state deviated linearly with respect to the other, you cannot have a linear contribution to the relative entropy, because otherwise it will be negative for one sign, let's say, of the perturbation. So it has to be at second order, the change in the relative entropy. It means that at first order, delta K has to be delta S. But this is interesting because it's very simple, but it's interesting because it somehow relates an entropic quantity that is, in general, is not an observable. The entropy is not an observable, it's a function of the density matrix, with something that it could be unobservable, for example, in the case of the Rindler case that is related to energy density operator. And this is the way, I think, people measure the entropy for thermodynamic systems, because you can measure the temperature, you can measure the energy, and then you can compute, let's say. Well, this has many applications, and in particular, recently, I'm not talking in this lecture about holographic entanglement entropy, but just I wanted to point out that this idea was used in holography to try to understand what is the meaning of Einstein equations in the bulk. So here, in the holographic context, this is Z is the holographic coordinate, and this is the coordinate of the quantum field theory. And these are like Ryuta-Kashanagi surfaces, measuring the areas. You measure the entropy, entanglement entropy of the region. And then if you take a conformal field theory in the boundary and spheres, the spheres can be conformal transformed to Rindler space, and you can get the form of the modular Hamiltonian, that is this expression for a sphere. You have to integrate for a position less than the radius of the sphere. And it's again the energy density times some number. And then you see that if you think you are perturbing the vacuum by some state, but very little, then you will have that the perturbation of entanglement entropy, the change of entanglement entropies, are given by these expectation values for all type of spheres of any size. But it all depends on this expectation value of T00 in some points. So you can see easily that the changes in the entanglement entropies for different regions, for example, here I'm taking a large region and very small ones, will be connected, because you have only this geometrical number there, but it's always T00. So knowing the change of the entanglement entropy for small things, you will be able to compute the change of the entanglement entropy for something large. And this connects the variation. So the entanglement entropy, the change of the entanglement entropy along this surface is related to the change of the metric around these points, because you have to compute the areas. So it means that the change of the metric around these points that are very near the boundary are related to some other points, the change of the metric inside, very, very deep inside of the bulk, So it means there is an equation of motion relating those things, and this equation of motion turns out to be Einstein equation. So somehow this, the way the entanglement is distributed near the vacuum is related to the Einstein equations. Okay, let me then continue. Then I'm using the other property of relative entropy, that is monotonicity.
For us, there is a question about Einstein equation or linearized Einstein equations.
Yeah, linearized. It's linearized. It's linearized around for small perturbations of the vacuum. Yeah, people have already like improved this in different ways. I'm not talking about that, but they have improved this in for example, putting matter inside, etc. So monotonicity of modular Hamiltonian, what we can do with that? How can we prove it? I will prove some inequality for operators rather for numbers. So the idea is that you take two regions. This green one is A and B is the larger one. So here are spheres, but it can be any type of region. So the algebra of B contains the algebra of A. And then by monotonicity of relative entropy, if I have two states and I compute the relative entropy in A, I can write it in this way: delta K minus delta S is less than or less or equal than the relative entropy in the larger algebra B. And you can do the same for the complement. So the complement, this is B, and this is B prime, is the outside part. This is A, and the A prime is the outside part up to infinity. And so you can see that B prime is smaller than A prime because it's a complement of a bigger region. So it's smaller. And then you can do the same. You can write the inequality of monotonicity for B prime less than the one for E prime, and express everything in terms of modular Hamiltonians and changes of entropies. Now, suppose that the global state rho 0 is pure. So you take some pure state there. And then we introduce this thing that I think I have already told about us. This is called the real modular Hamiltonian, or the full modular Hamiltonian. That is the combination of the modular for some region X, is the combination of the modular Hamiltonian for the region X minus the modular Hamiltonian for the complementary region. If you think in Rindler space, what this means is that you have half the boost operator acting on the right minus half the boost operator acting on the left. So this is the full boost operator. So this is a real generator of symmetries of boost symmetries. So this object has better properties than each of the parts. It in fact is an operator in the theory, in the sense of it's not a, let's say, operator value distribution or something like that. It's a real operator. And you can prove that for any global pure state, this combination annihilates the state. So it's a symmetry. As we have seen, for example, in the case of the vacuum, you have half a space, you compute the full modular Hamiltonian, it's just the boost operator that annihilates the vacuum. So this is always true, and it's quite easy to prove. And then if you take the rho 0 is a pure state, then you can put, for example, here Ka prime. You can add these two inequalities. You can add these two inequalities, and then Ka prime you can put the other side, and it's Ka minus Ka prime. So in this delta there is the quantities are evaluated in rho 1 minus rho 0. But in rho 0 they will vanish because of this property. So you get from summing this inequality something that depends on the left-hand side only on the full modular Hamiltonians evaluated in the state 1, not in the state 0, because the state 0 is this, and K's acting on the state zero are zero. On the right-hand side, I put all the entropies of the, I put all these entropies. And then again, all the entropies of the state zero vanish because you will get combination like this also for the state zero. But the entropy for a pure state, the entropy of some region is equal to the entropy of the complementary region, and then they cancel. So you get nothing about the state zero here. So you get this inequality that the only part where it appears the state zero is just in the definition of K, because these Ks are always defined for the state zero. So the modular Hamiltonians are for the state zero, but the state one can be completely arbitrary. Completely arbitrary. Oh, sorry. Oh. You can see that you can see in order to understand better what this quantity is, you can see that you can if the state rho one is also pure, this is zero. Because again, this cancel with this and this cancel with this. But this is not pure, you can purify it with some other, let's say, arbitrary, some other like artificial Hilbert space that I call Z here. And you can see that this quantity is just a difference of mutual informations between A and Z, and sorry, B and Z and A and Z, and by monotonicity of mutual information, this quantity is always positive. So you get that the difference of modular Hamiltonians evaluate the expectation value in some arbitrary state is always positive. So it means that these operators are ordered. This difference is a positive operator. It's always positive operator where B is a larger region than A.
So we got another question.
Yeah.
Is there a fuller version of the modular Hamiltonian which includes the boost generator on the patches F and P? In a black hole, this will be the interior and the white hole regions.
In the black hole, suppose you have an eternal black hole and you have your region is just the region 2, then your full modular Hamiltonian will be just the killing generator in the whole thing. It's just the killing generator. In flat space, it was just the boost generator here, but in the black hole is the killing generator.
Can I comment on my question?
Yeah.
Yeah, sure.
No, because you call something the full modular Hamiltonian, which in that diagram would include only the pieces of the 2 and 3, I guess, regions, but not the modular Hamiltonian, the boost generator in the 1 and 4 regions.
No, but it's automatic that because I'm writing, so these operators, I'm writing them at t equals 0. But then,
okay, so there is no 1 and 4
with operators. They act on operators here. If you let's say use them as generators for symmetry, exponentiate, and put u let's say a to the ik, a to the minus ik on each side of the operator, it will move this operator here also. Okay. Like
okay. Thanks.
So then let me show some application of this. The first one is just I take two half spaces, B and A. A is smaller than B. It's just translated some distance L with respect to B. So I can use that the modular Hamiltonian for B minus the modular Hamiltonian for A. That is just this is a Rindler modular Hamiltonian. This is Rindler translated some distance L. I subtract them, and it only survives this L piece with a plus sign now. That is integrated by T00 and in the full space. So it just gives you the energy, the full energy of the theory, times L, the distance, is greater than some combination of entropies.
Horacio, we got another question. So
yeah,
I
sure.
guess, I believe on the previous slide. So in the last inequality, I believe this is, do you have expectation value under which states? So which kind of expectation value are you taking? I believe this is
in this last inequality, there is no expectation value. This is just saying this, okay, this greater or equal than 0 means that this operator is a positive operator. It's a positive definite operator. It's just an operator equation. So it means exactly this, that the expectation value in any state is always positive.
Yes, I think this answers the question. Thanks.
So, well, and then this looks like, again, the Bekesten bound is not related to the original Bekesten bound or the thought experiment in the black hole. It's just, but it's a bit different, because here the energy is the global energy, and this quantity is always positive and vanishes for a pure state. It's something, this quantity is something like the entropy between B and L, but that is not entanglement with some other part of space. It's something entanglement with something else that is used to purify the system. I mentioned this because for me, I don't have a good understanding yet of this inequality, but perhaps because we don't understand much how it's saturated somehow. How can one saturate this inequality? Because its saturation comes from monotonicity, and it's more difficult to understand how does it saturate. So, but then let me go to another application that is more understandable, the result. Now let us take modular Hamiltonians for the form surfaces on the null plane. So it's like a Rindler wedge, but where I move the boundaries along the lines, the null lines describing the null plane. So we knew from last lecture that these modular Hamiltonians have, again, a local expression in terms of the stress tensor. And they only null line in each null line, they look like Rindler, where the point or the edge of the Rindler is just this point, the point gamma. So they look like this, integrated in the transversal direction. Now, if I take another curve, gamma, but it's deformed a little bit to the future here in some point, some arbitrary point, but only around some null line, and just deforming around a null line. And then I'm using the inequality that's saying that the difference of modular Hamiltonians is just a positive operator. But the deformation, it only deforms gamma for some particular y. And then all this part disappears, and then you only get the integral of t plus plus for all the null line, and only in one point y. So you get this quantity here, that is the integral of t plus plus in a full null line, arbitrary null line. And this quantity, this quantity has to be always positive, evaluated expectation value in any state. And this is what is called the ANEC, average null energy condition. And it's a very useful thing, because it has been proposed in the past, or assumed in the past for different things. For example, it is a part of the demonstration of some bounds on central charges, the Hoffman-Maldacena bounds. These are bounds that hold for the central charges of a conformal field theory in 4 dimensions, and you can obtain them from this inequality. So it has results also for quantum field theory. And then this type of inequalities have been proposed in the past, or assumed in the past, in many gravity theorems. In many gravity theorems, you have to assume some positivity condition for the stress tensor, and then to prove, for example, that wormholes are not traversable, or causality, boundary causality in ADS, etc. So now I'm going to describe another application of relative entropy, monotonicity, that is to prove somehow the generalized second law. The generalized second law, now I'm thinking in space-time with gravity, we have a black hole that is evolving. But of course, we are not proving it in the full gravity thing, but only in the limit where the Newton constant is very small, and you can think in a quantum field theory in a Curie space. So the idea is that you have the generators of the null lines generating the horizon, and they satisfy the Rajashuri equation that tells you how the area, the transversal area of these null generators change along the null line, the null direction. So this is expansion. This is called expansion. It's a change of the area in the direction of the relative change of the area in the direction of the null lines. And this gives you the Rajashuri equation, give you somehow the acceleration of the null lines to each other, let's say, in terms of this quantity that is again the expansion square. This is called the shear. That is give you giving you the deformation. It's not just expansion, but the deformation of the null surface of the surface as you advance in the null direction. And this is just the Ricci curvature. So using Einstein equations, Ricci curvature can be translated to the stress tensor. And assuming you are near the flat space limit in such a way that these things are second order, and you can neglect, because there is a square here, you can neglect these two things. Then what you get is that this equation, Rajashuri equation, give you the second derivative of the area, let's say, along the null direction is proportional to the stress tensor. So it means that the area as a function, now we can think we are foliating the horizon with different curves, and we are advancing, this is the null direction, we are advancing along the null direction in some particular way, any way that we want. And so we are computing the area, just integrating this equation, and you can integrate twice, and you get this expression that the area in this approximation is a constant times plus this integral that involves the stress tensor, because of Einstein equation. Of course, Einstein equation tell you that the stress tensor will change the geometry. And then what you get here is exactly the expression of the Rinder modular Hamiltonian for these deformed surfaces. So you can write it as expectation value of K. But then what is the generalized second law? What do we have to compute? You have to compute that the generalized entropy, the area over 4C plus the entropy outside. So we are thinking the area over 4C give you the black hole entropy plus the area plus the entropy in the outside part. If we move forward, you have the entropy of another piece of the outside part. So we have to prove that this thing always increases. But the generalized entropy, the part of the area, we have already converted to some quantum field theory object that is T mu nu, divided by 4C, eliminates this 4C. So we get in the limit something that is really independent of G. And then we have the entropy outside, that is a quantum field theory quantity. So it means the generalized entropy is a constant minus this difference that is just the relative entropy between the vacuum state and the state outside. And then as you move forward, the region outside part, in the outside part is always decreasing. This algebra will be smaller than this one because the diamond assigned to this is smaller than the diamond assigned to this one. So it means that the relative entropy will decrease, and it comes with a minus sign. It means that generalized entropy always increases. So you get it from monotonicity of relative entropy, also the generalized second law in this limit of semi-classical gravity. Well, it's only 10 minutes. So let me go through this calculation. So, this is just another application, let's say, of the first law of entanglement entropy. That is to compute the area term in the area term for a large region. So we already introduced the thing that the area term. Let's take some region that is very large, some large sphere, and we want to compute how the entropy will renormalize as we move to larger spheres. So we are computing the change of entropy between the state and the ultraviolet state to take away all the cutoff pieces. And this will give you something that is proportional to the area. There are other terms, but this will dominate for large radius. And we want to compute this coefficient here. So you can do this derivative, and it will be proportional to delta S times d minus 2, just because this radius, this size is to the power of d minus 2 because it's an area. And now we want to compute this delta S as a delta K. So how we do that? We do a small dilatation of the state that, for example, changing, you keep, we are doing, for example, the replica trick density matrix in Euclidean space, and we keep the size of the region fixed, let's say, and change the metric by some dilatation. It will turn out that this small dilatation will, in the partition function, just pull down some T mu nu, but as is a dilatation, it will give you the trace of the stress tensor. So when we compute through the first law the change under this dilatation of the entropy, it will give you something that is the expectation value of the modular Hamiltonian because of the first law, and the change of the state will be given by this integral along the points in the d-dimensional space of the trace of the stress tensor. Here K is the modular Hamiltonian of half a space, because we have a very large sphere that looks like half a space. And then you see that this part is that is coming from the ultraviolet conformal field theory is 0 because theta is 0. So you get only this. And then comparing, you can see that this integral has the integral of K that has a direction parallel to the Rindler edge, let's say. This integral give you the area again. So it will disappear when you when you compute just mu. So delta S will have also an area factor, will disappear from the equality, and then delta mu will be given by just this integral. And this is an expression of how it changes the area term as you get to the infrared. You can convert this thing using the conservation of the energy momentum tensor and invariance and translations and rotations to this expression that only involves these thetas that are the traces of the stress tensor. So it gives you this expression for the area term, for the normalization, the normalization of the area term. This can, in fact, this has always a negative sign because theta is always a positive thing because of reflection positivity. And what we have, we expected from the irreversibility theorems I described yesterday. But this quantity is not always finite. It is divergent if the perturbation that drives the normalization flow in the ultraviolet has dimension greater than d plus 2 over 2. You can see easily from the powers here in this integral. But it can also be finite in some cases. And then one interesting thing of this is that you can think that this normalization of the area term has to be related to the normalization of the Newton constant when the same fields are integrated out, because the same type of normalization will appear in the Bekenstein-Hawking formula for the entropy of a black hole, and then it will be taken, this coefficient on the entropy of the black hole will be taken as a change of the Newton constant. And in fact, there is an old calculation by Adler and C that give you exactly the same formula for the change of, except for the 4 here, you put the 4 here and you get the same formula. And it's the way the Newton constant normalizes when you integrate out fields. So again, we see a compatibility between quantum field theory and black hole physics, and in the limit of flat space, let's say. I think my time is quite over. I have 4 minutes for question because I don't want to enter into. But I this quantum energy condition, but you can read it from my my notes that are in the web page.
Okay, Horacio, thank you.
Okay.
Thank you very much. So it is virtual claps. So if anybody has questions, they can either write on the chat or directly ask, unmute themselves and ask. Seems to be no question.
Okay.
Maybe just I have a curiosity, Horacio, about this last formula that you were telling us. So from the QFT point of view, is this formula should have some approximation, no? It can't be true exactly, no? This renormalization Newton constant when integrating fields. So
well, I think what they do in this Adler's paper, they put gravity is classical, it's just a source.
Oh,
so
okay.
they put the quantum fields in an Euclidean manifold with some metric, and they integrate out the quantum fields, and it's supposed that this formula is exact in that case.
The quantum fields don't have a self-interaction.
They can have self-interaction.
They can.
Yeah. These thetas are the full traces of stress tensors, and in general, this formula is not easy to compute because it's non-perturbative. This is non-perturbative.
I see.
Yeah.
But the formula is exact.
Yeah, what they do is just they say, well, let's us expand the partition function in terms of the metric, and then they do variation of this partition function, and they start pulling down these thetas, and they realize that they can select in the effective action there will be many terms depending on the curvature, etc. And they try to select the term that has just the scalar curvature, the Einstein term, doing some particular variation of the effective action, and they get this formula.
I see. Thanks. Okay, so if there are no other questions, let's thank Horacio again, and we will have a break now and resume in 15 minutes. Thank you.
Okay.
Hi, Marco.
Hi, Mithat. How are you?
Good to see you. How are you?
Fine. I will be your chairman today.
Oh, that's great. I think, yeah, maybe, yeah, you should have been yesterday. Did I discuss quantum mechanics yesterday? I do not even remember. You know, kids take mind of everything. You know, so.
Yeah, but this is a sort of a random. I mean, it's up to, you know.
Of course.
There is no strict rule. Yeah.
Yeah. How are things with you?
Fine. Everything is okay.
Everything's okay. Good to hear. Okay, let me just move around a little bit. And let me do share screen and see if everything's okay.
Yes.
Okay. Can you see?
Yes.
Okay. Finally. Yeah, I talked about these quantum tilted potentials a little bit yesterday, and the potentials being deformed by an H-bar deformation, and well, that turns out to be the case if you have fermions in the game and if you integrate them out. But there is these nice papers of you and Giovanni and which do classical deformation, so sort of just classically tilted double wells. And the story changes quite a bit. And there is a way to go from one to another, but yeah, I didn't explore it yet. Okay. Let me see if I can also open. Okay, more. Let me also open chat window separately so that I can see what everyone says.
If you wish, I can also alert you when somebody writes in the chat if you don't want to get distracted.
Okay, so you can just let me know. So I can remove this thing so that it won't be disturbing. Okay.
So I guess we can start, right? So
okay.
I think we can start with third lecture by Mithat, please.
Okay, thank you very much. Again, it's a pleasure to be here. Today I will talk about some ideas concerning four-dimensional quantum field theories. In particular, I will talk about Yang-Mills theory with some mention of QCD with adjoint representation fermion. So the ideas I will talk about, I sort of outlined them in this page. The notion of adiabatic continuity and its relation to something called large n volume independence, And then from there on, I will go ahead and describe semi-classical solution of the form Yang-Mills in the on R3 times S1, and the emergence of the mass gap there and various other things, for example, multi-branch vacuum and stuff like that. And if time permits, I will mention a few things about IR renormalons versus bions, but if time is not enough, we can postpone it to tomorrow. Okay. So this is an aspect of Yang-Mills and many QCD-like theories that many of us are familiar. This is called asymptotic freedom. So as you go to high energies here, the coupling constant gets smaller and smaller. And as you go to lower energies here, you know, for QCD, for example, around 1 GeV, it gets larger and larger. So we say at short distances, the theory is weakly coupled and some aspects of it are calculable. But at long distances, it is strongly coupled. And a standard way to deal with such systems is lattice gauge theory and numerical simulations. But analytical methods are a bit more gloomy. So a fundamental question we can ask is whether we can find a regime of these asymptotically free and IR strong theories where non-perturbative dynamics become calculable. Okay. Now, this is where the idea of adiabatic continuity kicks in. Maybe there is a way to continuously connect a strongly coupled quantum field theory to a weakly coupled quantum field theory without any phase transition in between. So, for example, but the natural question is whether this is possible at all. It may not be possible, okay? So, at least on R4, I think it's a little bit strong statement to say that such a framework does not exist, maybe not very naturally. Because for the theory on R4, the theory becomes strongly coupled, you know, at longer distances. And in this sense, it doesn't matter if the theory is supersymmetric or not. But for example, you can consider the theories on a circle, R3 times S1. So something like that. And canonically, this is taught as thermal compactification of a field theory from R4. Okay, so it is like quantum field theory in 3 spatial dimensions at finite temperature, okay? And you can think of studying the dynamics as a function of the radius. And as I mentioned, as you go to smaller and smaller circle here, because of the asymptotic freedom at short length scales, actually the dynamics at the scale of compactification gets weaker and weaker. And some aspects of it are calculable. This is thanks to asymptotic freedom. But usually, many of the theories that we are interested in, probably all, have a phase transition as you go from high temperature regime to the low temperature regime. This is, for example, where we live, R4 in Euclidean description. You compactify it to R3 times S1, and usually there is a phase transition associated with free energy or some thermodynamic observables as you dial the radius of the circle. So in this sense, there is no natural notion here in the thermal context of adiabatic continuity. Okay. Okay. So this is what we have typically in nature, both in Yang-Mills, QCD, as well as other theories. Here I put only one phase transition, but there can be multiples. Maybe there is another one here, another one here. It's a possibility. The only thing is that there is a singularity as you go from small circle to large circles. Okay. And the thing that we want is a setup like this, where we have continuity between two regimes. Okay. Now, one can ask, you know, the roots of this idea, origin of this idea. In large N, so we are dealing, for example, let's say theories with SU engaged group, okay? So if you take large N limit, there is something called large N reduction, or it has multiple names, volume independence, or Eguchi-Kawai reduction, which is due to Eguchi-Kawai from 1982. And actually, it says something more stronger than adiabatic continuity, much, much more stronger. It says that a number of observables within the quantum field theory, a subsector of observables, are strictly independent of the compactification radius at large N if some condition holds. But it turns out that it is extremely tricky to achieve Eguchi-Kawai, very difficult. But it turns out also that it is possible, okay? And this notion of adiabatic continuity is sort of a cartoonish version of this large N reduction idea, but which works at finite N as well. Okay? Now, let me state, at least formally, what large N volume independence is. And you can think of it as a theorem because you can write the theory as a lattice field theory, lattice gauge theory, and you can prove this as Eguchi-Kawai did on lattice regularized theories, okay? But I will describe it in continuum. For example, take SUN gauge theory, for example, Yang-Mills, in toroidal compactification of R4 to R to the 4 minus D times S1 to the D. So you can take D equal 4. That means you can compactify it on T4. So there is no volume dependence in the large N behavior of topologically trivial single trace observables. For example, Wilson loops. Okay. And in their connected correlators, and if you want to discuss connected correlators, you better leave one-dimensional non-compact, T3 times R, some construction like that. And the important part of the story is provided there is no phase transition as the volume of space is shrunk. Now, you are in n equal infinity limits. You are always in thermodynamic limits. It means that you can indeed have, you are allowed to have phase transitions even at arbitrarily small volumes. That's perfectly fine because n equal infinity means you are already in thermodynamic limit. I repeated this because it is important. And more technically, there is a certain symmetry called center symmetry, which is described yesterday in Clay's lecture. Okay, it is a one-form symmetry, and as long as this symmetry, and when you compactify it, it is strictly speaking zero-form part of the story, is not spontaneously broken, and also translational invariance in lattice field theory is not spontaneously broken. It sounds very unlikely, but it is possible. There is an equivalence of observables. For example, you can calculate a very large Wilson loop on R4, and you can go and on the lattice reduce it to one side, okay? Then it is a string of matrices, but since matrices are non-commuting, this is really a string of unitary valued link fields. and combined just dimensional reduction of the field theory. And you can deduce, for example, if you calculate expectation value of this object in both field theory on R4 as well as in one-side theory, you can actually calculate string tension and they must agree. And string tension is a fairly non-trivial quantity because this is supposed to obey in confining field theories to area law, area of this, let me call this sigma, area of this thing. So, and you can deduce such quantity. And as I said, this statement you can prove, you can either use Largen, Schwinger-Dyson or loop equations or Migdal-Makenko equation, or use Largen classical dynamics. The big problem about this theorem is the provided parts, okay? So there is actually, for a long time, despite the fact that this is formulated in 82, it was immediately understood that it doesn't work because if you take Yang-Niels theory and compactify it at some scale like strong scale, there is a phase transition. And as you shrink the torus further, you go to a different phase. And there were some proposals of fixes around, again, early 80s. There was a flurry of activity up to 85. But some of these proposals are understood to be not quite correct between 2005 and 2010. Okay. Now, so the stumbling block is following. As I said, as you shrink the radius, there is always a phase transition. And to show this, to make this more technical, I think in the next page I will make this more technical. What you are doing is that there is an order parameter for the center symmetry. Maybe, let me go, okay. For example, take Yang-Niels theory, and I will go back there. On R4, it has a one-form center symmetry, Zn one form, this theory. When you compactify it on a circle, for example, just compactification on a circle, instead of just full 4 torus, this center symmetry reduces to a center symmetry in 3D, and a Zn zero form center symmetry acting on Polyakov loop on the compactified direction. Okay, so a zero form part and one form part. And a natural order parameter for the center symmetry is the holonomy of the gauge fields going around this circle. So this omega, trace of omega is exponential I A4 around this circle C. Okay, so this is omega, there's some path ordering here and stuff like that. And you can show that this object is charged under this symmetry. But I already told you at the very beginning that if you take Yang-Niels theory on a circle, it really has two phases. One of them, let's say this is R4, this is R3 times S1, this is beta direction, and this is beta critical. There is a phase in which this symmetry is unbroken, and there's another phase which is broken. So even the existence of basic, thermal phase transition tells you that this construction should not work, okay? And to show this, because at small circle, L less than L critical, this order parameter is non-zero, and you go to the confined plasma phase. Okay. To show this, you do a one loop calculation for the holonomy potential. And today in the tutorial section, Alexei will give a very intuitive derivation of this formula without using the tools of quantum field theory, actually, by just using StatMech. Okay, so I encourage all the students to check the tutorial because this is a very important formula in the game. It is derived in 1981 by Gross, Pisarsky, and Jaffe, and it is extremely important in thermal field theory, and it will turn out to be very important in my discussion today, okay? And the important thing is this overall minus sign here. It tells that the mass square for the Polyakov loop is negative, so it is tachyonic. It tells you that this symmetry is dynamically broken. Now let me go, sorry for my bad ordering skills. So this is this instability picture, okay? So if that potential, so that potential in all thermal field theory turns out to be negative. It's sufficiently small circle. So you can have a potential which is zero at first order in perturbation theory and perhaps to all orders. And for this idea of Eguchi-Kawai or large and volume independence to work, you want stability of that symmetry and you want that coefficient to be positive. This is what you want, okay? But as this picture indicates, it is almost impossible to achieve that. It looked almost impossible, but after you understand it, it is a triviality, okay? So this is the goal. And this is the holonomy effective potential on R3 times S1 for this Polyakov loop. Okay. And as I say, you may, you know, this is unavoidable in thermal field theory. You will necessarily go to this phase. The students may or may not be familiar with this potential, but they are certainly familiar with its consequences. For example, if you look to this potential, its minimum is at omega is some phase exponential 2 pi I k divided by n times identity matrix. K is 0, 1, all the way to n minus 1, okay? It has n minima. And if you go ahead and calculate the potential at its minimum, you obtain something that you know extremely well. You just plug it there and you just find that the minimum gives you the Stefan Boltzmann law for gluons. So it gives you free energy. It's free energy density, strictly speaking. And it is nothing but, you know, Stefan Boltzmann law. This pi squared divided by 45 to 4 is just, you know, blackbody radiation for photons, but now it is as if you have n squared minus 1 species of them, and this is what you obtain. So at least in the thermal construction, there is no hope of achieving adiabatic continuity or large and volume independence. Now, here is the point where the perspective changes. If you are familiar with supersymmetric gauge theories, you will know that if you compactify a supersymmetric gauge theory on a circle, not a thermal compactification, but on a circle, on R3 times S1L, now this is strictly non-thermal, mean that you are forcing the supersymmetric theory to obey a supersymmetry respecting boundary condition. That means that you are no longer dealing with the thermal partition function and your system do not have a thermal interpretation. And at least in supersymmetric theory, you are dealing with this graded partition function. So it is not a trace over Hilbert space, you know, without distinguishing bosonic and fermionic states, but it sums up over bosonic Hilbert space, but it subtracts off the contribution of the fermionic Hilbert space. So it is not usual thermal partition function. In the usual thermal partition function, this sign would be plus in the thermal case. And in this case, this is non-thermal and this sign is minus, okay? Now, actually, if you do this in supersymmetric theory, for that potential, V of omega, you always obtain 0. There is no, to all orders in perturbation theory, to all orders. Okay? This is interesting because it gives you some slight hope. But okay. But why is this possible? Why, you can ask, why is this supersymmetric theory? Is it happening because of some magical feature of supersymmetry? In some respect, yes, and in some respect, no. Actually, this thing is happening because this is the contribution of this term here, is the contribution of gauge bosons and ghosts, you know, but strictly speaking, gauge bosons when you do Faddeev-Popov quantization. Okay. When you do it in, say, minimal supersymmetric theory, let us take n equal 1 super Yang-Mills. So you have a vector multiplet, and vector multiplet is composed of gauge fields and gaugino, and there is an auxiliary field, which is not important for the story. And gaugino is an adjoint representation, which is important to our story. And there is also a gauge field. This potential is 0 because there is indeed a -1 coming from gauge fluctuations multiplying this formula. I am just taking this formula and writing the -1 part of it. But fermions, lambda, the periodic boundary condition, contribute strictly as +1, and it becomes 0. Okay. At that moment, a light bulb shines in your head, you know, some good idea comes to your head, and you realize that you can actually make this +1 +2. Okay, that means you can just introduce one extra flavor of adjoint fermion with just periodic boundary condition, and it's perfectly okay. And you don't even need to do any calculation at this stage, okay? And you learn that this calculation for the holonomy can have a positive coefficient, nf-1. And this center symmetry can actually be stable at small circle. This is a quite game changer now. And we know from history that some signs are more important than others, right? Go back to asymptotic freedom, you know, why asymptotic freedom was so important. It wasn't, technically speaking, an impossible calculation. Earlier on, you know, the calculation for the beta function was done for many QFTs, but the sign was always, so to say, in that case, positive. And people always believe that QFTs would have some UV pathology. This is something called Landau fault. But in QCD, what changed is the sign of that beta function, and it turned out to be negative. And it told you that the theory is actually UV complete, sensible at the UV. This is, in some sense, maybe in a lesser strength, something of that nature. In all the calculations that we did in this kind of setup, in compactification between 1980s to 2007 or something like that, the sign always seemed to be negative. But with this construction, you see that the sign can become positive, okay?
Mitat?
Yes.
Sorry. There is a question on the chat about whether the critical length is the inverse of the critical temperature, and why didn't you consider the critical temperature?
Yes, the critical, in the thermal compactification, let's say beta, in the thermal case, beta is inverse temperature, and this beta critical is really 1/T critical. It's important. Here, the construction is really on R3 times S1 beta, where beta is thermal. Okay? But in the other construction I am making here for non-supersymmetric theory, a good way to think about it is to think of it in Minkowski setup. And to think of it as R2, 1 times S1. Time is still as it is. Okay, you are not compactifying time direction in a Euclidean field theory and interpreting as temperature. Time is still as it is. So you take the theory on R3, 1 and compactifying one of the spatial directions. So you no longer have a thermal interpretation. Okay.
I have a question.
Yes.
Can you hear me?
Yes.
Okay. How much can you trust this computation of this holonomy potential? I mean, this is like one loop, no? So
yes.
Are you sure that the sign doesn't change, or there is no kind of instability if you include?
Yes. That's a good question. So higher order corrections to this thing are order G square. Okay. So higher loop corrections. And so, and in the small circle on the S1 beta circle, when beta lambda is much less than n, G square at the compactification scale, 1 over beta is much less than 1. G square beta is much less than 1. So these higher order corrections are there, but they do not change. They do not change the result. So, for example, they give a subleading contribution to free energy to this thing. These are really minuscule corrections in the weak coupling regime. They do not change the results. So it is completely reliable computation.
Okay,
but
I see.
If for some very delicate reason, one loop potential, you can make it vanish, the decision is made by two loop. You know, in supersymmetric theories, it happens that one loop, two loop, three loop, all of them vanishes, okay? And the genuine contributions come non-perturbatively, okay? But there are very delicate systems in which you can tune one loop to vanish, and the decision is made at two loop.
Bita, sorry, can I ask a question myself?
Yes, of course.
Which is based on the previous question. So yeah, this, if you take an F greater than 1, you see that parametrically at high temperature, you might be in an unbroken phase, like at 0 temperature. But then, since you don't have control of beta order 1, where you are strongly coupled, isn't it possible that you have more than one transitions and still you have... Yeah.
There is a possibility that maybe I will come to that. Okay. So there is a possibility that there may be some phase transition in between. Okay, so this tells you, let's say this is R3 times S1. The whole thing, it tells you that we know that we are in confined phase here, R4. And what we show is that in principle, there is actually possibility that there is some intermediate regime there in which the center symmetry is broken when beta is, you know. Actually, if you put to this theory mass for fermion, if you make fermions massive, okay, introduce mass of the fermion, sorry for, this is mass of lambda, let's say this is infinite. You can actually show that when mass is infinite, this is Yang-Mills. When mass is 0, for example, this is this QCD adjoint. The phase diagram, strictly speaking, looks like this. Okay. Here, the belief is that there is no phase transition. And again, this part is analytically calculable. Okay, calculable. And this is your beta of order 1, where there is a phase, L of order 1, L lambda of order 1, where there is a phase transition. So it is possible. But at least people check this numerically in lattice gauge theory. And the most recent update on that is that, at least, for example, if you do this with one adjoint fermion, super Yang-Mills, then you can achieve this adiabatic continuity for sure. And this is a result of lattice gauge theory. Of course, as theorists, who are doing analytic computation, we cannot really address this question. It is not within our toolbox. But our lattice friends who does numerical simulation can address that kind of question. So there is that possibility that there is some intermediate phase in which symmetry is broken again. But it doesn't change the fact that this regime can be continuously connected to that regime. Okay. But both are nice question. So one can ask the following question. Since you are going to small circle, whether this is dimensional reduction to three-dimensional theory or not, to two-dimensional reduction in which you take some three-dimensional coupling fixed. And the answer is no. You are really, the thing that is small and fixed is G squared at scale 1 over L is much less than 1, and this is fixed. So to take, for example, to reduce to a three-dimensional theory, you need to do, oops, I don't want that. You need to do 1 over G B squared is L over G4 squared L, and you have to take this fixed, and it's not that. But this is a technicality, never mind. So the theory is always locally four-dimensional. And I want to give some interesting intuition about this. So if it was the case that center was broken, this omega eigenvalues would all clump together, okay? Then this would be equivalent to the regular Kaluza-Klein compactification, where various modes comes in, various KK modes comes in units of 2 pi over L, okay? But whenever the eigenvalues are, whenever trace of omega to the power n is 0 for all n not equal to capital N, for not equal, n times k, the eigenvalues repel each other. If you look to the even perturbative spectrum, you discover something very interesting, and it immediately gives you why this idea of Eguch-Kawai works. You discover that if you write down the perturbative spectrum of the theory, it is no longer quantized in units of 2 pi over L, but instead it is quantized in units of 2 pi over Ln. Now it immediately becomes clear. In the traditional case, in order to go to L, L goes to infinity limit, R4 limit. So all of these modes, to capture the theory on R4, all of these modes must come down, and L goes to infinity and these modes become dense. But here, even at L fixed, you can achieve a continuum spectrum perturbatively, exactly as on R4, where we have continuous momenta, by just taking n to infinity. This is the perturbative intuition behind Eguch-Kawai reduction, large n reduction, but this intuition turns out to be working non-perturbatively as well. I will be talking about L fixed throughout most of my talk, and n fixed, and small, and small, let's say 2, 3, and stuff like that. And I will be mostly talking about in this regime where you have this discrete spectrum, and you can do some interesting semi-classics. We will learn that now, relating to our discussion in quantum mechanics and exponential integral, there are actually non-perturbative saddles in the game. These are called instantons, strictly speaking, monopole instantons, which will change the infrared dynamics of the theory in interesting ways. Okay? So I still want to say one thing about volume independence, because this is designed for students. I want to tell them something very intuitive. Normally, if you put a charge on R3, its potential decays as 1 over R on R3. Okay. If you insert a charge, its potential decays as 1 over R. So, but if you compactify this R3 R2 times S1L, and if you go at distances on R2, which is larger than L, you can use method of images, and if you look to potential at some distances larger than L, of course, we all know intuitively that it must fall to log R. It must reduce to log R potential, okay? And this is something that probably all of the students know from their electrostatics and stuff like that, and it is true. Okay? This is like point charge, this is like line charge potential, okay? Now, this 1 over R reducing for point charge after compactification to log R, and if you compactify one more direction, you reduce space to 1 dimension, it becomes linear potential. This is the reason that confinement is relatively easier in 1 plus 1 dimension. It comes out automatically. But what volume independence demands is something quite outrageous. It demands that, indeed, in 3 dimensions, the potential looks like that. You do compactification to R2 times S1L, and you even go to distances much larger than L. Now, one direction is shrunk. You forgot about one direction, but it still remains 1 over R, it demands, okay? And even if you go to 1 dimension, it still remains 1 over R. This is obviously incorrect in electrodynamics, and there is no way of achieving this, okay? But I urge you, as an interesting exercise, to derive this result by assuming that your gluons obey this spectrum, and in the continuum you obey you have this continuous distribution, okay, of the perturbative modes. Okay, so it really tells you 1 over R potential between 2 test charges. If this was for example, large N reduction for N equal 4 square Yang-Mills, which is a conformal theory, it tells you that if the condition of the volume independence holds, regardless of how much you compactify the theory, as long as one direction is non-compact and you measure the potential between 2 test charges, it is always 1 over R, 1 over X, 1 over distance. Okay? Now, and this is really a back of envelope calculation, or maybe for students, maybe 2-page calculation, and I encourage them to do. Now let me come back to this quantity, okay? Of course, any person who is familiar with supersymmetric field theory knows this quantity very well. This is actually celebrated supersymmetric Witten index, and it turns out to be extremely useful in this context, okay? The thing that is not sufficiently appreciated, maybe up until 2010, is that it is probably as useful in non-supersymmetric theories with the proper interpretation. It's really compactification of the theory, non-thermal compactification of the theory, where you probe the dynamics of the theory as a function of circle size, not temperature. And as I emphasize, regular partition function is just a state sum which doesn't distinguish bosonic state from fermionic state. You do summation over everything, but this thing is a graded state sum where you distinguish the two by their sign. And again, emphasis is that there is generically an instability, and in supersymmetric case there is marginal, and for n greater than 0, there is the stability of the center symmetry at small circle. Of course, if you have an F equals 0 theory, which is pure Yang-Mills and which is the subject topic of today's lecture, there is no way of achieving this. At least no simple way. Maybe there may be still a way that's fairly interesting, but at least no simple way. But you can do something, and that something at first sounds like you are doing a model, but in reality, that is not a model. And I am very optimistic that many interesting progress about Yang-Mills will come from this still. So you can take Yang-Mills theory, pure Yang-Mills, on R3 times S1, and on small circle regime where, this center is broken, you can add a double trace deformation of this form with sufficiently large coefficient A. And this thing can prevent, I should have a diagram, can prevent this center symmetry from being broken. So you can restore center symmetry. But this thing, action is, remember, in large n counting is order n square. And this object here in large n counting is order n square. So it is not a small perturbation. It is like you are taking a hammer and you are hitting your theory on the head with this hammer. It looks like you are doing something uncontrolled at first, naively. But the story is far more interesting than that. So, and you can ask whether this thing changes the Hilbert space structure of the theory and various structure of the theory. As I said, it's a deformation of order n square, but it turns out that it is something fairly interesting. After stabilizing the center, at least in the large n limit, it turns out that the effect of this object on observables, such as mass gap of the theory or string tension of the theory, is 1 over n. I hope from the students, new generation students, to appreciate this couple pages, because I think it is fairly deep and not yet sufficiently appreciated. And the reason, the way to see this, one way to see this is following. You can write down Schwinger-Dyson equations that you are familiar from your QFT classes. But now you can write them down for Wilson loops in lattice regularized theory. If you know Schwinger-Dyson equation already, and if you have taken a standard class in QFT, you do, you should. There is no difficulty in generalizing to lattice field theory and write it for Wilson loops, okay? And these are also called, they have multiple names, loop equations, or after Migdal and Makinko, they also called Migdal-Makinko equations, who did it first in lattice gauge theory, okay? And you can write down loop equations for Wilson loops. You obtain some, loop is equal to some small deformation with tiny plaquette coming from lattice. Okay? Question, what is the effect of this deformation? Obviously, the existence of this deformation will change these loop equations, okay? So what it will do is that whenever this variation acts both on the loop as well as on these double trace operator, it will sort of stitch them to one another. So there will be extra terms. There will be extra terms like that. So they are not the same. So naively speaking, they cannot be the same. But at large n, if center is unbroken, and you can guarantee this by tuning this A to be sufficiently large, you can use large n factorization. And this is this disconnected part times connected part. This is the connected part. Connected part is order 1 over n squared. But now comes the merit of this double trace. Each one of the terms in the double trace, which is single term, trace omega, is charged under center symmetry. So these things are actually strictly zero. Okay. Now you learn that in the deform theory, the loop equations are identical with the original Yang-Mills theory, provided the deformation is large enough. Okay. So then, of course, solution of these things are same. Hence, okay, I already described, and there is a very nice quote that I like a lot from Gabriele Veneziano. He said something like, "Oh, it is like a good Samaritan. It does the good deeds, and you do not even know it existed." Okay? So this is the idea of volume independence. But now, instead of volume independence, let me go to finite n, and let me put this deformation. Okay. And this is my deformation A. So then this construction as I said, if A is sufficiently large, you can undo the phase transition, and you can go to a confined phase, which in the sense of order parameters continuously connected to Yang-Mills theory on R4. Okay. Now, this you can think as analytic continuation of the confined phase to arbitrarily small circle. Now, what happens? And this is the regime where the dynamics becomes calculable and interesting. It's always interesting, but it is not always within our grasp. But now what happens? So in this regime, in the small S1 beta regime, S1 L regime, L lambda is less than 1. Strictly speaking, L lambda n is much less than 1. Actually, all these trace omega to n is 0 tells you that you have this configuration for the holonomy. But holonomy itself behaves like an adjoint Higgs field. Okay? And it pins down eigenvalues at the roots of unity, and they have now fairly small fluctuations. It tells you that the dynamics abelianize. This is similar to Polyakov model as well as Seiberg-Witten theory, in both of which dynamics abelianize in the same way. Okay. So to all orders in perturbation theory, you can show that there are n-1 massless photons. But photons, massless photons, in long distance three-dimensional theory, in 3 dimension are equivalent, they only have 1 degree of freedom, and they are equivalent to a compact scalar. It's called, the compact scalar is called dual photon. And you can, and this dual photon is supposed to have, strictly speaking, it is really n-1 dimensional vector, but let me not worry about that, is supposed to be gapless to all orders in perturbation theory. Okay. And you can ask the following question, whether this gaplessness is protected or some non-perturbative effect render it gapped. Okay. So this is the abelian duality. Let me write abelian duality in 3D. You can map both magnetic field as well as electric field to the language of this dual photon. And in the system, let me go and come back. Sorry for that organization. There are these monopoles all around. Let me go back. Sorry. There are monopoles, and these monopoles are finite action monopole saddles. These are genuine saddles. And they have finite action, which comes out to be 8 pi squared divided by g squared n. And they proliferate in the vacuum, similar to our quantum mechanical example where instanton proliferates in the vacuum. Okay? And one can show that, I show this in gory detail in my lecture notes in the PDF file that I posted on Slack page. They generate a term like this. But even without thinking about this technically, which you can actually deduce, which for here at the bottom generates a mass gap for dual photon, which is non-perturbative. But even without knowing technicalities of this discussion, you can actually deduce that this has to be the case for the following reason. You have a proliferation of monopoles, so you have a magnetic plasma. And if you put, for example, you can put an external magnetic probe or electric probe, okay? Let's say you put a magnetic probe to a magnetic plasma, and this is really like a magnetic conductor, if you wish. But we know from the Debye mechanism that he did in the context of electric charge, the electric charge in vacuum has a potential 1 over R, but when you put it into a plasma, it decays as, R divided by C as R, as a Yukawa. So in a plasma, the field decays as 1 over R. Okay. So it tells you that the system must acquire a finite correlation length, and this correlation length is mass gap inverse. Okay. So, and here, if you insert an external magnetic charge, you will see that its field decay exponentially fast and with a finite correlation length, and you deduce that there has to be a mass gap. This is Polyakos mechanism. Okay. Now, you can also think inserting an electric charge, okay, here, Q electric. And in the language of the dual photon, this corresponds to a vortex of the sigma field. This is a vortex of the sigma field. So this vortex is, vorticity is the electric charge. And you can do this as an exercise for a unit electric charge. You can take such a vortex. As you go around, it has to, you know, give you, as you make circulation, it has to give you electric charge. And if there were no monopoles, the electric field, you can show that must obey, since we are in 2+1 dimension, must decay as 1 over r. And the potential must decay as log r. So somebody is trying to sabotage my lecture, as you can see. Just let me, yeah, that's your name. So from here, you can actually deduce that when you incorporate monopole instantons into the dynamics, instead of the potential between two test charges being log r, it becomes linear confinement. And you can show this step analytically. Okay. But I will not describe that in gory detail. The only thing I will say is that you can write down the monopole operators in general. As I said, these monopole instantons are saddles in the problem. For the general SUN theory, they are associated with the affine Dynkin diagram, and there are n types of monopoles, okay? And their action is instanton action, usual instanton action, which is 8 pi squared divided by g squared divided by n. And proliferation of these events can generate mass gap and non-trivial things. And this sigma is the dual photon. Since they have a topological charge 1 over n, theta dependence appears as theta over n. And this p is omega center symmetric, 0, and exponential IE, the fluctuations of the holonomy field around the center symmetric minimum. So the monopole operator has a dependence to both dual photon as well as holonomy fields. Okay, but for our discussion in Yang-Mills, since the holonomy decouples, we can forget about it and just pay attention to the dual photon. Okay. As I said, these monopoles proliferate in the Euclidean vacuum. They are there, plus charges, minus charges, and once in a while they come in pairs, similar to our quantum mechanical discussion. And these pairs, you know, according to my lecture in quantum mechanics, they have to be interpreted as critical points at infinity, and these are really dominant configurations on the tymbals of those critical points at infinity. And you can write a description like that, okay? Okay. I knew, you know, that I did some organizational mischief, but so this is what I was saying. If you put an external charge, due to device screening, it decays exponentially. Sorry about that, okay? And again, the Euclidean vacuum needs to be interpreted as a grand canonical ensemble of classical monopole plasma. Okay. Any questions at this stage? Okay. But now we can write down the long distance effective theory, which is valid for L, which is valid L and lambda much less than 1. And as you go to long distances, this is the Maxwell term for n-1 photons. And this is the term that comes from monopole operators. And I neglected theta angle and stuff like that. And the monopoles are associated with the standard root system plus an affine root. I should mention that this affine root is here. Normally, if you were in the 3D Polyakov model, you would have alpha 1 through alpha n-1 on the same footing, and you wouldn't have alpha n on the same footing. This affine root is present because of the topology of your adjoint X field. It's a compact field. If you wish, in this picture, sorry about that, if you interpret monopole alpha 1 here, you know, these eigenvalues fluctuating and touching each other, monopole alpha 2 here, you know, fluctuation of the eigenvalues and touching each other, you see that alpha n here is on the same footing with the rest because of the compactness of your adjoint X fields. And it has some very interesting implication now. We can also put here theta angle dependence. Here you can insert theta over n. Okay, and now extremize this action functional and look to ground state properties as well as mass gap. If you calculate mass gap, you obtain something quite beautiful, actually, and convert it to the strong scale. Mass gap turns out to be mass gap square, strong scale square, lambda ln to the power 5/3, and it is a multi-branched function of k. Okay, and for the mass gap in the genuine vacuum, you have to take a maximum over these branches. Okay, so it is like some structure like that, and you know, some and mass gap lives here as a function of theta angle. So at least the mass gap here is a monopole instanton effect. And again, to distinguish from Polyakov model, of course, if you are in a genuinely 3D theory, then there wouldn't exist a theta angle like this, and you wouldn't have this multi-branch structure. And in this case, the mass gap on R3 times S1 beta is an effect due to monopole instanton. It has this expected multi-branch structure and non-triviality associated with it. This is something fairly non-trivial, actually. And if you pay attention to the case of SU2, you see that you have cosine theta plus 2 pi k over 2. You see that at theta equal pi, actually mass gap vanishes at leading order in semi-classics. Monopole instanton term vanishes. I need maybe a couple minutes to wrap up the story. But then you can actually, what happens at second order is you have this term, but coefficient of this comes out to be this. But at second order, S0, you generate a term which looks like exponential minus 2s0 in semi-classics, and it is independent of theta angle. And this is something called a magnetic Bion term, something which is magnetically charged, but topologically trivial. It has, you know, second Chern number 0 and non-trivial magnetic charge. And you can show that in this term vanishes at theta equal pi, it is 0. And the other term within the fundamental domain, 0 to 2 pi, has two minimum. So this is nothing but spontaneous CP breaking realized in the semi-classical domain. Indeed, on R4, we believe that in pure Yang-Mills theory, we have a CP symmetry at theta equals 0 trivially and at theta equal pi non-trivially. And there, this CP is spontaneously broken. And here you see this explicitly, that it is the case. Let me not go other things. I wanted to mention some lattice results and stuff like that. Maybe I can go to those things in tomorrow's lecture, starting from there. And probably I should stop here. So in this theory, to wrap up, in this semi-classical domain, we can obtain vacuum energy density as a function of theta angle. It's a multi-branched function. Mass gap is a function of theta angle. It's again multi-branch function, and things like topological susceptibilities and stuff like that. And all of the properties of this theory in the small circle regime seems to be adiabatically connected to the large circle regime. Now, there is actually ample lattice evidence that these statements are true for the pure Yang-Mills theory and the Fermi-Yang-Mills theory at this stage. And I am optimistic that much more progress can be made concerning these theories and their connections to R4.
Thank you very much, Mithat. So, very nice lecture.
Thank you.
So, given that we have a long break, maybe we can still collect a few questions. Again, either direct.
Can I get a cup of water? Otherwise, I cannot talk. 10 seconds.
Okay, okay, sure.
Okay, sorry about that.
Okay, no problem. So maybe in the meantime,
can I ask a question?
Oh, yeah, please.
Oh.
No,
yeah,
please,
sorry, Mithat. This is a very basic question about the earlier part of your lecture. But could you say one more time what is the precise definition of volume independence in terms of correlators of single trace operators?
Very good. For the correlators, okay, first of all, let me actually about that. Let me, so, okay. So if you just look to the expectation value of, say, some, I don't like this color, and of some, say, some Wilson loop, W of C, on, say, R4 or some lattice regularized, lattice theory, lattice regularized, okay? And look to its expectation value, okay? Then, you can write this as, okay, let's say this is X, U, X in the one direction, X plus 1 hat in the X plus 1 hat in the one direction, so and so. You can write this, the whole thing with their spatial dependence. You can write this on the lattice all the way around. Now, if you reduce this to a one-side lattice model, this is just string of matrices. Something like here, it will be U1, U1, actually many of them. Then let's say this is two direction, U2, U2 with no spatial dependence, U2, and U1 dagger, dagger, and U2 dagger, U2 dagger. You erased, you removed all of these spatial dependence. Okay. If you calculate this with the one-side model action and one side, and here our action is Wilson action, okay, is sum over all plaquettes, is boundary over plaquettes plus complex conjugates, And here action is really, it is just one side. It is really, you know, action is sum over mu nu, u mu, mu less than mu, minus beta, u mu, u nu, u mu dagger, u nu dagger. If you calculate this thing in this one-side matrix model, the results are these two observables match, okay? But now you ask also about connected correlators. So if you look to, if you want to learn about connected correlators, you have to leave at least from R4, you have to make a reduction to 1 cube times R kind of reduction. So reduction to quantum mechanics. So if you have a Wilson loop here, let's say, and Wilson loop there on the, or some tiny plaquette here and tiny plaquette there, which are separated in this time direction, let me call it tau, and look to their connected correlators, this on 1 cube times R tau, this has to be equal to the theory, to the same construction on R4, provided center is unbroken.
And by connected, you mean the leading piece that you get after you subtract the factorized
exactly
result.
Exactly.
Mm-hmm.
Let me put these things as that, and you forgot about this connected part. And if you wish to make this have a nice scaling in the large n, you know, order 1 scaling, maybe you have to put some numbers of n here, so that, but this thing
right.
will decay exponential minus global tau here. It will have an exponential decay like that. And actually, provided center symmetry is stable, this is true. So you can derive this mass gap from quantum mechanical system. And there are other observables, but the precise sense of observables is following. If you ask questions about, you know, when you do this compactification, as I said, there is zero form center symmetry. You have to ask questions about observables which are singlets under, which are neutral under this zero form center symmetry. In string theory context, these are called untwisted operators. So untwisted. And the operators that do not have a matching are called twisted operators in string theory context. Okay? So for the untwisted observables, there is no volume dependence. These are the observables in the neutral sector of the theory under this global symmetry. And for those, you can actually derive, derive these things. If you let me, I want to say one more thing on that. Actually, some people in Italy, you know, Massimo Delia and friends, look to not center symmetry, but something more non-trivial, topological susceptibility. They even have some very exciting results confirming what I said here in lattice. But what they did is following. Let me tell you this picture. It is very, very interesting to my mind. It's quite fascinating. They did simulations of the theory in zero temperature. They used to do that all the time in the past. And you obtain some zero temperature topological, T equals 0, topological susceptibility. And they look to the ratio of this with double trace deformation, but now beta lambda is less than 1. So beta is like 500 MeV inverse. Okay, so they go to a circle size which is extremely small, which is like, you know, the confinement scale is like 200, and it is, in some sense, it is, if this is beta, the confinement, which is lambda inverse, they go here, okay? And they calculated this topological susceptibility in the presence of this double trace deformation. And look, if you do not put this deformation, it falls down like that. And this is the result of dilute instanton gas or something like that. But if you put the deformation up to errors, it is 1. It tells you that there is something extremely deep about this theory on either on R3 process 1 and even in one-side theory. So my suspicion is that if you can solve the theory on R3 process 1 in the large N limit, that's actually in certain respect will give you the solution of the theory on R4. You can, if you show in the large N limit of this construction, the mass gap, that will be the same as the mass gap the theory on R4. It will not differ tiny bit. As surprising as it may sound.
Okay, thank you.
Thank you.
Hi, I'd like to ask a question. So in the last slide that you showed us, you computed the mass gap for the particular small, for the particular small lambda ln limit, right?
Right.
And
correct.
we would like to extrapolate from this to the, let's say, to the Young-Mills theory, the undeformed Young-Mills theory, or even just the large L limit.
Right.
How can we do it? I mean, what in this formula will remain true when we go to the large L limit?
Okay. So I can tell you my expectation. Okay. So this is semi-classical domain. And if you just look to the mass gap, this is the mass gap for, gauge fluctuations, and it has lambda ln to the power 5/6. Lambda times lambda ln to the power 5/6. So it grows. But there is also W boson mass. W boson mass is like 2 pi over ln. And this brings me to the region of validity of effective field theory. Okay, this is a very, very good question. And if you want to insert here lambdas, put a lambda here, put a lambda in the numerator. So lambda 2 pi, it is really lambda times lambda ln to the -1. So this is lambda ln. So this is decaying. You can see that these two things, first of all, EFT is based on maybe there is a hierarchy of scales. Of scales here. Okay. So the effective field theory based on monopole instantons is based on this hierarchy of scales. Okay, let us, and it is only valid, this formula that I derived is only valid in this domain. Then lambda ln is less than 1. Okay? But let us proceed with that. You know, if you naively extrapolate that, the W boson mass becomes comparable with the dual photon mass. Strictly speaking, the thing that we call glue ball, which is generated by trace F square, is actually a 2 sigma state. There is some technicality that I skipped. These dual photons are actually still charged under, transform under center symmetry, because if you construct them in a gauge invariant way, they turn out to be charged under center symmetry. But you see, trace F square involves FF, and each one of them is a sigma. And the sort of glue ball, my intuition is that this must transmute to this thing that we call glue ball, okay, glue ball mass. But within this formalism, we cannot address this question, okay? So within the effective field theory. So, but on the other hand, let me tell you one more thing. If you can find if you can understand this transition domain, you understand everything literally, because from here on, there is volume independence. at least at large n. That mass gap must be vanishing. So if one can understand this transition domain from semi-classics to strong coupling, one can actually probably solve mass gap problem. Okay. But within the power of our formalism, we do not know here what to do. So our effects, our formalism is valid only in this range. And so an idea I had, actually, everything I present in these lectures are historically in opposite order to the order that I did these things, because, you know, it's a funny thing. But an idea I had later on was perhaps maybe in this domain, small circle domain. So we calculate mass gap, okay, mass gap, and maybe we can, there is this mass gap square, S0 effect, and there is probably minus 2 S0, some fluctuations around it, some fluctuations around it, 3 S0, some fluctuations around it, so on and so forth. So maybe I hope that, you know, mass gap, first of all, if these resurgence ideas are true in quantum field theory, and I have I think that they are true in the semi-classical domains for sure. Maybe I hope that maybe one can, if one had enough information, one can try to sum up these trans series and then try to extrapolate that. But the honest answer to your question is I do not know how to go from this regime where lambda ln is less than 1 to this regime where lambda ln is greater than 1. This is a big question mark. But if somebody understands it, at least to my mind, they can make it sufficiently rigorous to solve it mass gap problem for young males.
So maybe it's time to close. So let's thank Mithat again.
Thank you very much.
So we will reconvene at 5 with Clay. Okay.
Kyriakos, can I tell you something? So is this
sure,
recorded?
please. I think it is recorded, but I don't know if we need to record it. Can we turn off the recording for until 5?
Or I can call you in private. It doesn't matter.
Yeah, sure.
It is
Yeah,
okay. Let us. I will send you an email. Then we can chat. Okay.
Sure.
I'll send you an
please,
email. Okay.
Please. Okay.
Now I need to take care of the kids. I forgot for a moment, so I need to. Okay.
Right.
Okay. Thank you very much again.
Thank you. So.
Bye. Stop share. Leave.
Ok. Sì, già, no, andate.
Hi, Clay.
Hello.
How are you?
Fine. As fine as anyone can be.
Yes, I'm the chairman. So in a minute we will start.
Okay, very good.
Just let's wait a little. Okay, so I guess we can start. So, okay, we can have now Clay's third lecture. So Clay, please.
Okay, thank you very much. All right, welcome back, everyone. So when we left off last time, we were discussing, what were we discussing? We were discussing SUN Mills and the fact that it has a ZN one form global symmetry. And we learned that the charge of a Wilson was equal to the n-ality of the associated representation, which I remind you is equal to the number of boxes. Mod n. And this was a good quantum number precisely because in SUN Yang-Mills, there's only adjoint matter. So we cannot screen, we can only screen things which have boxes that are, number of boxes that are equal to n. Okay, so what I'd like to tell you now is that this is intimately related to confinement. And in fact, the connection of one form symmetry to confinement is main reasons to study one form. Okay, so what's the punchline? So one form symmetry gives a crisp way, let's say, to characterize confinement. So what will be the statement? So the statement is that we have this Zn one form symmetry, and just like any other symmetry, we can ask if it is at long distances spontaneously broken or preserved by the vacuum. So option 1 is that it is spontaneously broken. And this turned out to be synonymous with being deconfined. And on the other hand, the other option is that the one form symmetry is preserved by the vacuum. And this is synonymous with the theory being confined. So this is a very nice statement. I'll explain it in just a minute, but you know, it's very nice to have a clean, symmetry-based understanding of what it means for a gauge theory to be confined or deconfined. So, okay, let me give you a sketch to understand how this works. So usually the phases of a gauge theory are discussed versus by considering a perimeter versus area law. For a Wilson loop. So let's draw a picture. So we consider a fundamental Wilson loop. We have it in the past connect up like this, and in the future connect up like this. So this distance here is R. This is a space-time diagram. This distance here is T. We look at the expectation value of this. This is a fundamental Wilson loop. And there are two characteristic behaviors. One is that this expectation value was like e to the minus perimeter. And in this case, you usually say this is deconfined. And then the other possibility is like e to the minus area. And then you say this is confined. Okay, so what does it have to do with this one form symmetry? So basically what we're going to do is that we just say that for large R and T going to infinity. So we take R to be very large and we take T to be even larger and going to infinity. We have essentially this, this loop is falling apart into two separate lines. You see the lines are very far separated because R is very large. So we view this as a sum of lines. One from each side of length T, which is going to infinity. And what is the statement? If the theory is confined, that is, if the area law holds, then this infinite Wilson should have expectation value 0. Meanwhile, if the theory is deconfined, this infinite Wilson line, non-zero expectation value. Now, I should make a comment here, which is that you see you have this e to the minus perimeter term here, and you think that the perimeter is getting very large, and so why aren't you also getting 0 on the infinite straight line in the deconfined case? And the reason is that the perimeter behavior on the line that can be absorbed by a counter term on the line. So I'm imagining that I've added to the line a counter term to make the perimeter behavior disappear because the perimeter is proportional to the length. So that's easy to do. So here we've added a counter term. Counter term to absorb the perimeter term. Okay, so we can easily translate the usual discussion of area versus perimeter law into this statement about infinite straight Wilson lines. Okay, and now to see the connection to one form symmetry,
Clay, we have somebody, I guess, wants to ask a question. So please.
Yeah.
Two questions. One, why is it a straight line vertical? Why is it not horizontal? Because couldn't one say the same thing that?
No, R is large and fixed, but T is even bigger and going to infinity. So the influence of the two segments of the two lines. You usually think of the Wilson line in this limit as like a quark anti-quark pair that apart at a large distance r.
Okay.
And that's the same. That's the point of view that I'm taking.
Okay. And second thing, so what exactly is this counter term that soaks up the perimeter?
It's just a counter term that's proportional to the line element on the line. So that's clearly a local term on the line. Right. The perimeter is equal to the integral of the line element. So that's a local term that you can add on the line.
I see. And the same cannot be done for area because it encloses the whole thing. Okay.
Exactly.
Thank you.
Great questions. Okay, so let's see the connection to one-form symmetry.
Clay, sorry, there is another question, I guess, again, so with this counterterm. So why this counterterm makes sense? The operator is still charged under the symmetry in a clear sense? This is the question.
I didn't quite parse the second part of the second clause.
Okay, so the first is why this counterterm makes sense. This is the first part of the question. The second part is the operator, which I'm not sure I understand which operator is referring to, is still charged under the symmetry in a clear sense. Is the operator still charged under the symmetry in a clear sense?
Let me just reiterate what I said to the previous question, which is that a counter term is anything that looks like a local term that you can write down modifying the operator. So we're discussing here a Wilson line operator. And when we're normalizing a Wilson line operator, we should ask what kind of local terms can we write that are local integrals over the line. And one such term that we can write is just the integral of the line element, which measures the perimeter of the line. So saying that there's not too much really fundamental about saying that there's a perimeter law that can be absorbed by this counter term. So it's cleanest if we use that to just absorb that counter term, to absorb that perimeter law. So that's what I mean when it says it makes sense. Okay, so let's consider the connection to one form. So the main thing that we should note is that this infinite line is charged under the one form symmetry. Right, going back up here, we discussed that the charges, the objects that are charged under the one form symmetry are Wilson lines, which have a number of boxes that is not equal to 0 mod n. And here we have the fundamental that carries the minimal unit of charge. And so it will not be surprising to you that this Wilson line having an expectation value is break or not the one form symmetry. So let's be even more precise. What is the one form symmetry generator? So we're going to look at some U alpha of sigma, as we've introduced in the last couple of lectures, where sigma intersects the line once. So if we're in R4, which we may as well be for this discussion, we could imagine sigma is just R2. So we put the one form symmetry on an generator on an infinite plane. We let the Wilson line pierce the plane. So that means that the Wilson line is going to be charged under this one form symmetry. And then have a kind of canonical situation in spontaneous symmetry breaking, where we see that these phases are distinguished by a charged object having a VEV. So that's a very nice conclusion. The one form symmetry is really telling us about its status in the infrared as broken or unbroken, is really telling us about confinement, telling us about this basic question in phases of gauge theories. So that will be a quite useful perspective, and that's really one of the main reasons that I am studying this this subject, is because all the details straight here might help us understand confinement of gauge theories. Okay, so any more questions about this before I move on to the next topic?
I have a sorry, I have a question. Can you hear me?
Yes, I can hear you.
Yes. So following the tutorial yesterday, and also the discussion here, I was wondering. I was wondering about this. Sorry, this observer. That imagine that we have local operators along with like non-local operators like this Wilson line or truth line. Is it possible to extract the non-local part from this correlation and then drop out the local operators?
I'm not sure I completely understand this, but maybe your question is about the fact that we're studying non-local operators and what's their connection to local operators. Is that kind of the spirit of your question?
Like imagine that like for example, we have a correlation function that's the Wilson line and some other local operators, O1, X1, O2, X2, and so on. Then if one wants to like calculate this correlation, is it possible to calculate this and then drop out the local operators from this correlation, or other way around, drop out the...
Okay, I understand what you're asking. I understand what you're asking.
I see.
So the answer is no. So the ward identities that connect that are the generalized ward identities, where you can say the analog of replacing the divergence of the current with something else, is just that you can manipulate topologically the U's in the correlation function. So if you have a correlator involving U's, you can do something to it. But here we're discussing the correlation function of the line. The line is the charged object, not the symmetry generator. Okay.
I see. Okay, thanks.
Any other questions?
So I had a quick question. Can you hear me?
Yes, I can hear you.
Okay. So do I lose something if I think of having the Wilson line wrapping a one cycle like an S1, and that is like a local order parameter when you dimensionally reduce? So it's like a normal symmetry breaking, or is...
Well, do you lose something? Well, you can... it's more like you gain something in the sense that if you put your theory on a circle, you'll gain another scale in the problem, which is the radius of that circle. And if you look at the Wilson line wrapping that circle, you might be able to say you can treat it as a local order parameter in the limit where the circle is small. But if you want to assess the phase behavior of the theory in the limit where the circle is large, it's best to treat it as the line.
Okay.
Okay. All right, so let's keep going. So I'd like to move on to a new topic, which is defects and backgrounds. Okay, so we have discussed in these lectures so far, we have discussed symmetry via background fields. In the lecture, I talked to you about a partition function that was a function of a variable, which was a background gauge field. And we have now also, in the second lecture and just now, discussed symmetry via symmetry defects. What are symmetry defects? These are these things U alpha of some manifold M. So these topological operators. And it's very natural to ask, what is the relationship between these things? So in fact, as I will explain now, there are one and the same points of view. So symmetry defects are really the same thing as background fields. So which you choose to use is up to you. They're really going to be equivalent. Okay. So what is the idea? So let's begin. So let me draw a symmetry defect so we can see what's going on. So here is some particular symmetry defect UG. Let's start in the simplest case of zero form global symmetry, that is ordinary global symmetry. Now this UG is like a domain wall. It has codimension 1, so it cuts. So this D cuts space-time into two pieces. And I will suggestively, instead of calling them pieces, call them patches. So what we would like to do is we're going to think of, so there's a natural one cycle to consider here, which I'll draw. We can call this one cycle gamma. So gamma pierces this UG. And on the left, we'll think of this as patch 1. And on the right, we'll think of this as patch 2. And the way to make a connection, what we'd like to do is to make a connection between this UG, this insertion of this symmetry defect operator, and a background gauge field. How will we do it? So we'll think that at P1 intersect P2, this is UG, there is a transition function. Associated with group element G. So G is the group that's labeling this symmetry defect. What does that mean? A little more concretely, it means that there is an associated background gauge field, we'll call it A, which has the feature that if you integrate e to the IA gamma, you get G. So this is the background gauge field. Okay, so what happened? So on the left-hand side, there's no background gauge field. There's just a symmetry defect. And on the right-hand side, I have explained to you how to introduce a background gauge field A that we can canonically read off from this configuration. So it's a gauge field A, which has holonomy G when I go along this cycle gamma. So let's say that a little more formally. So let's let G be a discrete symmetry group. We don't have to be doing anything fancy. You could think G is Zn. So what's a background gauge field for G?
So there is a question about whether gamma, you are thinking gamma to be infinitely long?
This is a local picture. So I can imagine this happening in a compact geometry, but all that's important is that gamma intersects UG once. That's what's important about this picture.
Gamma is a cycle, so it's closed or not?
Yeah, imagine this is happening inside a compact inside a compact space, if you like. But so you don't have to worry about anything going on at infinity. The significance of gamma is that it intersects UG once, and that will be made clear in the following statement. Okay, background gauge field for G. What is that? What does it mean to activate a background gauge field for a discrete symmetry? So first of all, what is it mathematically? So the easiest thing to think is that it's an assignment of holonomy. The holonomy is assignment G in the group for each cycle. Let's call the cycle in space-time. Now, we can't, we're interested in gauge equivalence classes. So what is the gauge equivalence class? We'll call the equivalence class bracket A. What kind of mathematical object is it? So it's a cohomology. H upper 1 means it has degree 1 on space-time. So this M is space-time. And it has coefficients in G. So this is cohomology valued in G. So this might look fancy, but I stress to you that H upper 1 of M with coefficients in G, that's just a widget that eats a cycle and gives you an element in G. So it is closed. If we think about cohomology, it's closed. What does that mean? That means that the holonomy exp I integral of A along gamma equals 1 if gamma is a boundary. So trivial cycles, homologically trivial cycles get trivial holonomy. That's a requirement. And it's a cohomology class because we're modding out by gauge transformations. This means modulo exact stuff. Okay, so that's just a little flash about what is mathematically a background gauge field for a discrete symmetry. So, you know, you're doing the Ising model. The Ising model has Z2 global symmetry. What does it mean to turn on a background Z2 gauge field? What is the data that you have to pick to even specify a background Z2 gauge field? Here I have defined it for you. Now we come to the precise statement about the relation between defects and background. They are related by Poincare duality. So, okay, we start with a class A in here. That's the background field. And then we can apply Poincare duality. What will that do? That will produce some class sigma. Where would it live? So Poincare duality relates cocycles and cycles. So that will be a D-1 homology class with coefficients in the same group. So D is the dimension of space-time. And this sigma here, this manifold that pops out of this is where the symmetry defect is. So that's the mathematical relationship. That's what underlies the statement that background gauge fields and symmetry defect operators are one and the same. So in the previous lecture, I told you that you could define global symmetry in quantum field theory, introducing these topological operators, implementing the symmetry, these symmetry defect operators. And now you can see that an equivalent definition would be that you can define symmetry in quantum field theory by explaining how to couple to background gauge fields. And those are the same idea. Okay, so now that we have this, it's not too hard to see what you should do for higher forms. By the way, I should tell you that I will unpack this in some examples momentarily. So hang on if it seems too abstract. So the same idea works for Q-form symmetry.
Today we have another question.
Yeah.
Please.
This is also true for continuous groups, right? You're just taking discrete group for.
No, so for continuous groups, I was going to say that later, but let me say that for continuous groups, there's something that I'm omitting. So there was a question about whether this is true just for discrete groups. And as I have stated so far, it is true just for discrete groups. For continuous groups, we are restricting here to flat backgrounds. So those without any curvature. You see, the definition that I've given you here is telling you that for a discrete group, all the information of a background gauge field is global. There's nothing local. It's just about globally what are the holonomies. And for a continuous symmetry group, when you discuss a background gauge field like U1, of course, you know that there's also local information, like what is the curvature at a point. And so the special, the simple restriction that I've given you here will work for continuous groups, but you have to work in the narrow class of backgrounds where F is 0.
Okay, thanks.
But again, I want to stress that for continuous global symmetries, we're not really confused about what are the right notions of gauge fields and stuff like that. The sort of really tricky part of this story is what's going on for discrete stuff. Okay, so the same idea works for discrete symmetries. Sorry, for Q-form symmetries. So let's say what it is. So if we have a Q-form global symmetry greater than 0, we'll have a background field will be some B, and the class of B, where will it live? It will be in H upper Q plus 1 of M with coefficients in G. And this G will be the Q-form symmetry group. So I'll put a superscript Q. And of course, you could think that exponential, whenever you have such a background field, exponential of I gamma, which is a Q plus 1 cycle, B, this is the Wilson surface. So it's the analog of holonomy. And again, defects encode backgrounds. The Poincare dual of a background gauge field B is equal to cohomology class sigma, homology class sigma, where will it live now? It will be in HD minus Q minus 1 of M with coefficients in G. And so this is the symmetry defect locus. Again, so the picture is similar. It's just that the dimensions seem different. So we can have, let's draw an example just so you see we're on the same page. So here, for instance, let's now let this smaller thing, if we're talking about a Q-form symmetry, then UG of sigma has higher codimension than 1. So let's let that line be UG of sigma. And then the Poincare dual is here. And so this is where you would measure in this discussion, this would be gamma Q plus 1. This is where you would measure the holonomy. Okay.
Do you have to restrict G to be abelian, or can G be non-abelian?
Excellent question. So this actually was discussed in the tutorial yesterday, but for those that were not there, so if Q equals 0, G can be any group. And mathematically, H upper 1 of M with coefficients in G makes sense for any group, abelian or not. If Q is greater than 0, G must be abelian. And this is actually true for the higher form symmetry itself. So this is not a restriction on my formalism, but in fact, the higher form symmetry is necessarily abelian. So I encourage you to think about it for a minute. It's very similar to the way you would proving that is very similar to the way you would prove that higher homotopy groups are abelian. You can prove it pictorially using only the topological property of the symmetry defect operator. So that's a good little exercise. So I'll leave it. Okay, so that was a lot of formalism. Let's see some concrete stuff. Okay, so our favorite simple example is the Maxwell theory. For the Maxwell theory we discussed yesterday has a one-form symmetry, which is U1 electric times U1 magnetic. And the electric current is mu nu, and the magnetic current is star F mu nu. So how do we write the action coupled to backgrounds? Okay, so we've got an integral F mu nu. I'm being a bit sloppy, but that's okay. But now we're going to introduce a two-form background BE mu nu. And that will couple to J electric mu nu, which is F mu nu. And then we also have a B magnetic two-form B mu nu, which will couple to star F mu nu, like that. So this is, I've omitted some 2 pi's and some e's, but this is how you couple the one-form symmetry to background fields. And if you look at this, this is just standard AJ type coupling, right? We just put the currents and we put a general background gauge field and we contracted the indices. So here, BE and BM are two-form gauge fields. And their gauge transformations are simple. So BE shifts to BE plus D lambda E, and BM shifts to BM plus D lambda M, with the parameters now lambda E and lambda M locally one forms. Okay, so that's one example. So we can couple Maxwell theory to these two-form gauge fields, and we can compute a partition function that depends on these fixed backgrounds. Okay, give you another example, discrete example, more in line with what we were talking about above. Let's do 3D U1 Chern-Simons theory at level K. Okay, so what is the action? S is K over 4 pi integral of A wedge dA. And I claim that this has ZK one-form symmetry. So let's unpack that a bit. Okay, so I'll do some of it, and then I'll leave a piece of it as an exercise. So, well, why? So what is going to be the conserved quantum number? Well, we can measure the charges of Wilson lines. Now, as we discussed in the Yang-Mills example or another in the electromagnetism example, one-form symmetry, the charged objects are lines. So if there's a good quantum number measuring the charges of lines, that's a hallmark. That's telling us immediately that there's a one-form symmetry. But there's a little catch here that if you think about the charges of Wilson lines, well, this looks like it should be Z-valued. Right? After all, can't I introduce a Wilson line with an arbitrary integer charge? And is that arbitrary integer charge a good quantum number? Here I said that there's a ZK one-form symmetry. So the key is that there's a screening effect. So you can consider a monopole operator. Right, what's a monopole operator? Oh, it's a configuration where the integral of S2 on S2 of F is not zero, where the S2 surrounds O. So in Chern-Simons theory, the Chern-Simons term, which is like K integral A dA, says that monopoles have electric charge K. And of course, these monopoles are dynamical. We sum in the path integral over F. So these dynamical monopoles can screen the charge of a Wilson line. So that means only the charge mod K can be screened. You see, this is very analogous to the situation we discussed in 4 dimensions where we had charged matter. And if the charged matter had some non-minimal charge, then instead of killing the one form symmetry completely, we kill it down to the minimal multiple of charge. So this here reduces a naive U11, this is the naive answer, down to the true symmetry ZK1. So how would we couple this to a background? What do we do? So is K over 4 pi integral A dA. And now we add 1 over 2 pi integral A wedge B. So this is going to be the background. Okay, so an interesting exercise. Which is basically just some little manipulations, but it will check that you know everything that's going on here, is to check the reduction to ZK at the level of the background fields. So what does that mean? It means that you say that B, big B is say K times some B, where little b has integer flux. Periods. And you want to prove that this is trivial. That is, in this case, you want to prove that it's equivalent to putting on no background field whatsoever. Okay.
Sorry, I had a quick question if I could.
Yeah, sure.
So you're saying that in even in abelian theory without matter, you can.
Sorry, you cut out a minute. You cut out for a minute. Can you say that again?
Can you hear me now?
Yes, I can hear you now.
Yeah, so you're saying that even when you don't have any charged matter, just have operators that are charged, you can have a screening of screening effect in the theory.
On the line, yeah.
On the line. Is it also true in, say, U1 electromagnetic theory? Something like this, if you just don't include fermions there?
Well, there's no charged matter there. There's no charged operator.
Okay.
Yeah, so there's nothing in addition to check.
So it's very unique to the Chern-Simons theory.
Yeah, the Chern-Simons term is tricky, right? The Chern-Simons, the fact that the Chern-Simons term couples the electric and magnetic charges together is a little bit tricky. Yeah.
Right. Thanks.
Yeah. Any more questions? Okay. If there are no more questions, then I'll to another really important example, which is the SUN Yang-Mills. So as I have beaten over your head several times, we know that this has ZN1 one-form symmetry, and this is related to confinement. So it would be nice to understand more concretely, how do we couple this quantum field theory to a background field? So what's the background? Okay, well, it should be a field in the second cohomology group of space-time, whatever it is, with coefficients in Zn. And we'll see, as I'll describe to you below, this is very closely related to bundle topology. By bundle topology, I mean when you're studying gauge theory, instantons, magnetic fluxes, all these things are important, and they are pieces of bundle topology. And we're going to see that this field B is also of that form. So in order to get going, we're going to have to do a little bit of an interlude on bundle topology. So let's do that. So let's start with a simple case of SU2 and SO3 gauge bundles. Okay, so what labels the topology of an SU2 or an SO3 gauge bundle? So an SU2 bundle is labeled by an instanton number. Okay, so what is the instanton number? Let's call it I is 1/8 pi squared. This is one of those factors that you should commit to memory. Trace F wedge F. And it is an integer. Okay. So when we consider the path integral and we're doing SU2 gauge theory, what does it look like? Okay, so of course, you have an integral over the space of connections, and you have e to the minus s Yang-Mills here, which depends on A. But this is not enough. These connections, this is a continuous variable. These are connections on a fixed bundle. So in addition, we also have the sum, a discrete sum, over the instanton number. That is the topological type of the bundle. Okay, so we have these two steps. We have the integral over the connections, the continuous part of the field variable, and then we have a sum over the discrete bundle topology. So that's SU2. Now, what is the difference between SU2 and SO3? So SO3 has more gauge bundles. So let me underline this, more. So in addition to instanton density, there is now a new topological invariant. So let's call it, I'll tell you the full terminology. So if you see this in print, you don't get scared. The second Stiefel-Whitney class.
Clay, there is another question. Maybe.
Yeah. Go for the question.
So when you do the sum over instantons, sum over bundle, wouldn't there be, or couldn't there be some another weight coming?
Yeah, so that's a good question. So there is another weight. I've suppressed it into the action. It is the theta term, right? There's a theta F wedge F over 8 pi squared. So if you remember the first lecture, I introduced the theta.
Okay, yeah.
And since the instanton number is quantized, that's telling you that you're weighting each instanton sector with a phase. So indeed, there is such a term.
Okay, thanks.
Okay, so we're discussing SO3. SO3 has more gauge bundles. In addition to the instanton number, there is a discrete magnetic flux, which is mathematically called the second Stiefel-Whitney. It is denoted W sub 2. And what kind of object is it? It's an H2 of space-time with coefficients in Z2. So this is a Z2 valued magnetic flux. Why do I call it that? So first of all, the fact that it's Z2 valued just means that if you take W2, you can integrate it on any 2 cycle, sigma 2 in space-time, and this is a number mod 2, so it's either 0 or 1 mod 2. To explain this terminology, Z2 valued magnetic flux, let's do a special case. For example, let's have A, the SU2 bundle. So we'll write it as A sub A in components, sigma A over 2. These are the Pauli matrices. A equals 1, 2, 3. And let's imagine that only A3 is non-zero for a moment. Let's look at that special case. Then I claim that the integral of sigma over sigma 2 of W2 is in fact equal, this is one way to define this quantity, is equal to 1 over 2 pi integral dA3 mod 2. So you look at you look at this special U1. So A3 is like the carton. It's like the U1 inside SO3. We look at that U1, a special connection there, and we can evaluate the standard magnetic flux. So this is just the standard field strength of that. We compute, so that would be the magnetic charge if it was a U1. We take it mod 2. And that's the value of this second Stiefel-Whitney number. Okay, so if you're evaluating this for a standard monopole, well, you have some 2-sphere S2, you divide it into 2 patches. So this is the north half where you have A3 in the north, and here you have A3 in the southern half. And the difference between them is some gauge transformation d theta, where of course e to the I theta of sigma 3 is the gauge transformation relating the patches.
Clay, it has been asked if there is another formula for W2 in terms of all the A's.
In terms of all the A's?
Yes, when they are all non-zero.
I don't know of a very simple formula for that. There might be one, but I don't know one offhand. There's a, yeah. Let me think about it. I might come up with something. Okay, so so this is, so if you plug in, so this discrete magnetic flux would compute the winding number of this gauge parameter theta. That's a standard. You compute the winding number mod 2. That's the standard way of measuring magnetic charge. And what I'd like you to note is that SU2 double covers SO3. This is a double covering. So if the bundle is an SU2 bundle, then if you think about this magnetic monopole construction that I just wrote down, then what we would need is that theta is in fact 2 times some phi. So in that situation, what we would conclude is that W2, which is the integral over S2 of dA3 over 2 pi, that this would be equal to the integral around the equator of 1 over 2 pi d theta, which would be 0 mod 2 in this situation, because theta would be twice something. So we have the following, although I've proven it to you only in this special case, we have the following general result. So the general result, SU2 bundles are the special case of SO3 bundles where W2 equals 0 as a cohomology class. Okay, so now we can say, what is SO3 path integral? How does that differ from the SU2 path? So as usual, we have integral dA over the continuous part. We've got the action. We have the sum over instanton number. But finally, we've got a second sum if we're doing SO3. We've got the sum over W2 in H upper 2. So that is the difference between SO3. If you've always wanted to know what is the difference between SO3 gauge theory and SU2 gauge theory, where does the global form enter into the partition function? And what you can see here is that it doesn't enter locally. Locally, we only see the integral over A. And that's the integral over A, the continuous part, is what controls the perturbation series. But where we do see the difference is in the bundle topology, which controls the non-perturbative effects. Okay, so let me just...
There is another question which is about what happens to the one-form symmetry of SUN when you introduce fermionic matter.
Very good. So let me actually, I need to say kind of one.
We are actually, running out of time, in fact.
Yeah. So let me conclude, and then we'll come to that question, which is a little bit in a different direction. So let me just say that the SUN is similar. So the SUN story is similar. So what does that mean? SUN bundles are labeled by the instanton number, which is again an integer. SUN mod ZN bundles have an additional invariant. Again, we call it W2. It's in H2 of manifold, now with coefficients in Zn. And the SUN, sorry, this is supposed to be mod Zn. Mod Zn path integral includes a sum over W2. Okay, so I'll stop here. for the day. And next time we'll explain how to use this to activate the background fields for the one-form symmetry in SUN. What does all this have to do with that? And we'll finally prove something about the dynamics of SUN. Okay, thanks.
Okay, thank you, Clay.
Okay.
So I believe we have only the time for just answering the question that has been asked in the chat about fermionic matter.
Okay, so so the situation there is extremely similar. So first of all, it doesn't matter if it's fermionic or bosonic. That's not relevant to this discussion. The situation there is basically identical to what we discussed in the case of U1 with charged matter, where we discussed that adding charged matter can screen Wilson lines and therefore break the one-form symmetry. So if we have fundamental charged matter, for instance, in SUN, we can screen any kind of Wilson line we like, and so we break the one-form symmetry completely. But if we add special charged matter, then maybe some piece of the one-form symmetry will survive. So imagine, for instance, we were talking about SU4 Yang-Mills, where the one-form symmetry is Z4. And suppose we make dynamical only matter in the symmetric tensor, symmetric rank 2 tensor with 2 boxes. So then we can't, however many pairs of that matter we produce, we can't screen the fundamental. We can screen things with multiples of 2 boxes, but not with an odd number of boxes. So in that case, we would break the one-form symmetry from Z4 to Z2. And the general story is very similar.
Okay, so since in a few minutes we will have the tutorial by Alexei starting, maybe we can thank Clay once again and postpone to, well, I think last lecture will be on Friday, right?
Yes, last lecture is on
Yes,
Friday.
very good. Okay, so Clay, thanks a lot.